Hello, my name is Daraja Brown, and this is my Lab 5 video report. In this lab, I studied the motion of a falling slinky. The purpose of this lab was to observe and explore the connection between the slinky's motion and the forces that are related to it. The physics principles I used were the momentum principle, or equivalently Newton's second law, formulas for gravitational, tension, and drag forces, as well as the velocity and position update formulas. For this lab, I used tracker software to analyze the experimental data obtained through the video, Python to create a computational model of the object's ideal vertical motion based on tracker data, and Excel to create a comparison of the observed versus predicted model. Here are my main results. While the predicted and observed Y positions started out and ended at the same time, the values in between differ considerably. There are various potential reasons for this, which we will discuss later. For this experiment, the first step in performing the lab was to identify the system and surroundings. My system is the bottom of a metal slinky, and the surrounding is the earth, ground, air, and the upper part of the slinky, which provides the tension force. For the experiment, I utilized a YouTube video suggested in Canvas. I then used the tracker software to obtain data about the motion of the the slinky. I set the origin of the system at the bottom of the slinky and calibrated the distance with the height of Derek Muller, who is the man on the left. On his Twitter, he stated that he's about 1.75 meters tall. I oriented the axes and coordinate system for the positive y-axis to be pointing up. Then I went frame by frame through the video to mark the eraser's position over time. Tracker generated a table showing time and its corresponding x and y position coordinates. Based on the tracker data, the initial position is 0, negative 0.000853, 0 meters, and the initial velocity is the 0 vector since the slinky starts at rest. The final y-coordinate was negative 0.531 meters. After obtaining this data, I transitioned to Python to create a computational model of the predicted motion of the slinky. Using old start codes and editing them, I input the initial conditions for position and velocity that I just shared, as well as the slinky's mass of 0.225 kilograms according to my research. I set B equal to 1.604 in the end for the drag force based on trial and error. I then created 2 while loops instead of just the one that we had in an old lab. The first while loop models the portion of the slinky's motion where the top of the slinky is falling but the bottom is not, which occurs when the tension and gravity forces are equal and opposite, and they're the only forces occurring. The second while loop is when the entire slinky falls towards the ground, which involves the force of gravity and drag force as the net y forces. I updated velocity and position in both of these cases. Again, here are the results of my experimental data and computational models comparison. The y values were consistent at the beginning and the end, from 0 seconds to around 0.28 seconds, and then again at about 4.8 seconds. The y values during the bottom of the slinky's fall, however, were quite different. One reason this could have occurred is due to the fact that I only tracked 13 points in tracker, so the curve was not as precise as it could have been. I also could have misclicked during tracking, which would have skewed the data, or there could be additional forces acting on the system that I did not consider in my model. What if a mass was added to the bottom of the slinky? The same trend in motion would occur since the spring would still initially have tension force opposing the greater force of gravity, and the bottom of the slinky would stay stationary until the top reached it. And if a mass was added to the top of the slinky, the shape of the slinky's motion would still have a similar shape, although the whole slinky would start to drop faster, considering that the mass at the top would add additional gravity force from the beginning, and it influences the tension force. Overall, this slinky dropping lab further elucidates how forces interact and how changes in those interactions affect objects and their movement. Thank you.